Alright, hi guys. So this is going to be a review video for Exam 3. So Exam 3 is going to be online through Canvas. It's not up yet. I'm just going to level with you guys. I haven't finished it yet. At the point that I'm recording this video, which is on March 15th. So at this point I haven't finished it yet. I've had to tweak some things because I had planned to have Chapter 16 on Exam 3, but because of the extended spring break, now Chapter 16 is going to be on Exam 4. Chapter 18 has been removed. So now, here we go. Exam 3 is going to cover the second half of Chapter 13 on eating behaviors, Chapter 14 on sleep, and then Chapter 15 on emotions, aggression, and stress. So the exam will be in Canvas when it's time for you to take it, and there'll be a link to that. If you go to modules and you have material for Exam 3, you'll see that link there. That's also where you need to go to do activities. You'll see the activity assignments there as well. So my intention in this video is to give you a brief review. I do have the slides I can pull up so you can kind of see where I'm getting this information from. But as always, if you have questions, email me. So as far as Chapter 13 goes, let me do this here so you can see both of these. Okay, fantastic. Alright, so with Chapter 13, now this is my updated study guide where I took out Chapter 16. If you got the old study guide, it would have the exact same thing. It would just have Chapter 16 included, but Chapter 16 is not going to be on this test. So this is my updated study guide that you can find on Canvas. So when it talks here about basal metabolism, that's talking about the energy that you have to stay alive, to maintain homeostasis. It talks here about heat production. You want to stay the right temperature, membrane potentials, things like the sodium-potassium pump. That's very important. So a large chunk of the energy that you get from food, your body is using just to maintain homeostasis. And then you're also using some energy for digestion itself is a process that requires energy, and then also extra behaviors, right? Okay, conversion of glucose to glycogen and glycogen to glucose. So we have this chart here, this picture you can see, that glucose is the energy that your body likes to use, and that your brain can use it without insulin, but your body requires insulin to use it, which means that a person who has diabetes is going to have issues. More on diabetes in a second. So what we said here is that glucose can be converted into glycogen through a process that involves insulin. So once again, insulin is very important to take glucose to glycogen. Why would we want to convert glucose to glycogen? Well, glycogen is more easily stored, so we can store that in muscles and things and then use it when we need it. And so then, if you have stored glycogen, you want to break it back down into glucose you can use, then the hormone glucagon is important for that. So insulin, glucagon, both hormones that are important here. Now, if we're talking about insulin, somewhere in here we have diabetes. Here we go. So we talked about how type 1 and type 2 are the more accurate terms. Technically, type 1 is usually something that happens in children, or starts in children, but it is possible that a person could develop type 1 diabetes later in life. And then when you talk about type 2 being adult onset, that's usually how it happens, but children can start to have type 2 diabetes now as well. The major difference is that type 1 is usually more severe and has to be treated with insulin. So this is where the body stops producing insulin, versus type 2, where the body is not able to use insulin as well, and so there's a reduced sensitivity here. Sometimes type 2 diabetes can be controlled with just a change in diet, exercise, that kind of thing, although sometimes it does require medication, and it is associated with sedentary lifestyle, being overweight, that kind of thing, okay? Different structures that you need to be thinking about: the ventromedial hypothalamus and the lateral hypothalamus. So the ventromedial hypothalamus is thought to be the satiety center. So this is the part of the brain that causes you to feel full, so you know when to stop eating, versus the lateral hypothalamus is the hunger center. Lets you know when you need to eat. Now, the arcuate nucleus is going to be an important portion of the hypothalamus. We're thinking homeostasis, we're thinking hypothalamus, and it's especially important because it produces hormones that help control all of this. Just like how the hypothalamus produces hormones that control the different stages of sleep, it also has hormones that control the different types of hunger and satiation. So this is going to be important for then producing these substances that are listed here, hormones related to hunger and satiation. So fat cells produce leptin. This is your body's way of keeping track of how much fat you have. And you need a certain level of fat. A certain amount is healthy. So if your body has lots of fat cells, then it will produce lots of leptin. And that will tell your brain, okay, we've got enough fat. We don't need to be hungry anymore. However, if an individual has damage to these genes so that their fat cells don't produce leptin, then they may still be overweight, but their brain doesn't know they're overweight because there's leptin's not there to trigger that, and so the individual might continue to feel hungry and overeat. So you see we had the exact same thing. Both of these mice had a problem with their leptin production, but the difference is this mouse was treated with leptin versus this mouse that was untreated, and you see what happens here, okay? Now, with ghrelin and PYY336, the major distinction here is, are they making you feel hungry or are they making you feel full? So ghrelin is something that's going to be an appetite stimulant. You think ghrelin, growth hormone releasing. It's causing you to grow. It's causing you to be hungry. Although you can see issues with ghrelin in individuals who are obese. It may be that even if an individual has eaten a full meal and it's time for their ghrelin levels to fall, they may remain high. They may still feel hungry. And that could be a biological cause for someone overeating. Okay? PYY336 is going to work in the opposite way. It's going to be an appetite suppressant. Okay? And let's see. I feel like that's most important bit there, but what I did want to say here is that ghrelin and PYY are shorter term. So your ghrelin and PYY336 levels go up and down throughout the day versus leptin, because leptin is produced by fat cells and your number of fat cells don't change very quickly, then leptin is more of a longer term control, not something that changes a lot during the day. Okay? And then eating disorders, we talked about anorexia, bulimia, and binge eating briefly, about how with anorexia we have a person that is engaging in the purges without the binges. So we tend to think of purging as being vomiting, but it doesn't have to be. This could be fasting excessively, which is sort of the definition of anorexia, or excessive exercise, that kind of thing. These individuals severely deprive themselves of food, so because of that they tend to be significantly underweight. There are all kinds of health problems that are associated with that, but there does seem to be an issue with viewing themselves realistically. They tend to have very negative views of anyone who has any amount of body fat at all. Okay. Bulimia is going to be a combination where you have the binging and the purging. So what may happen is a person may feel anxious or stressed, and then eating helps them to feel better, and they eat a whole lot in a short period of time. Then they feel guilty. They want to try to undo that, and so they engage in purging, which could be vomiting, laxatives, but could also be, as I said, fasting and extreme exercise, that kind of thing. And then binge eating would be the binges without the purges. So this is an individual who eats well above the amount of food that is needed to have that basal metabolism. Okay. So that's a brief overview of chapter 13, or the portion of chapter 13 that's going to be on this test. With chapter 14, we talked about different types of rhythms. So a circadian rhythm is going to be a rhythm that's about 24 hours. So circa is about day, so about a day there. We also talked about other types of rhythms. So let me see where we have this, the differences between the rhythms. So we have infradian rhythms that's going to occur less than once per day. You see this here, so that could be something like menstrual cycle, that kind of thing. Ultradian is going to be multiple times a day. Let me see, here we go. So maybe like eating behaviors, hormone release that can kind of go up and down throughout the day as well. So a rhythm is going to be something where we have a pretty consistent pattern to when this behavior occurs. Now, we feel like we've figured out where the biological clock is. We have this suprachiasmatic nucleus. Where am I here? Here we go. The suprachiasmatic nucleus is something that we believe is important for circadian rhythms, only for circadian rhythms, not for other types of rhythms. This is the rhythms that are about a day. So we know that when we do a transplant of this circadian clock, or the SCN, then that causes the individual that received the transplant to have the same circadian rhythm as the donor, right? For lack of better terms, okay? Now, as far as our clock goes, if we were left to free run, which means we didn't have any kind of input from the environment, our free running natural schedule is a little bit more like 25 hours. So we had this research study where a person was isolated from any cues about the time. And what we found is that they started to naturally drift later and later in the day. So we tend to have a free running period of about 25 hours. As far as stages of sleep go, we talked about how you have non-REM sleep. We have 3 stages. We used to have 4, 3 stages of non-REM sleep, where an individual can have some eye movements, but they're not rapid. They're kind of like slow rolling of the eyes, and your muscles are not paralyzed, so this is where you do your flopping kind of thing. Versus REM, rapid eye movement sleep, where you do have the rapid eye movements, obviously. You have a very active EEG, so the brain almost looks like it's awake. This is when dreaming occurs, and the person can be, supposed to be paralyzed. Their major muscles, like breathing, that's still happening, but like their core muscles for movement, I try to say moving and movement at the same time, and anyway, for movement, are supposed to be paralyzed there, okay? So yeah, so this is beta waves. We're awake, we're paying attention. Then we have this stage 1 sleep. So we go from beta, which is awake and alert, to alpha, which is awake but drifting to sleep, and then stage 1 is the first stage of REM. So as you go into a deeper sleep, you'll start to see that these waves will become a little less organized, a little larger waves, very slow waves, but large waves. So this is slow wave sleep, non-REM 3 sleep, very deep sleep. And then you go into REM sleep, where the person is technically paralyzed, like most of the muscles are unresponsive, but you have an EEG that looks like a waking person, or almost looks like a waking person, okay? As far as sleep patterns goes, we talked about how for young adults, one thing is that you spend a lot of time in stage 2 sleep, but then stage 3 sleep is something that's going to be greater towards the beginning of the night, and then later in the night you tend to have more REM sleep. So we're supposed to fall into non-REM 1, non-REM 2, non-REM 3, and then REM. Non-REM 1, non-REM 2, non-REM 3, and then REM. And you often have a brief awakening after the REM episodes as well, even though you may not remember that. Okay. Nightmares versus sleep terrors. The difference here is what stage of sleep is it happening, and what's that experience like. So we had this creepy picture. You guys remember the creepy picture? What we're going to see here. Oh yeah, babies sleep a lot, but don't sleep a lot. It's kind of weird. They do sleep a lot, but there's not any kind of consistent pattern that would be helpful for parents. And as you get older, you tend to sleep less, especially stage 3 sleep, which is that deep sleep. Kind of goes away here. Let's see, where's our, somewhere in here. Anyway, it's in here somewhere. You'll find it. Nightmares versus sleep terrors. Nightmares are going to happen during REM sleep. Sleep terrors are going to happen during non-REM sleep, often during non-REM 3. So with sleep terrors, it's hard to wake the person up. They may be panicking, maybe crying. They don't remember a specific dream, though. They're not sure why they're scared. Versus a nightmare happening in REM sleep, the person wakes up and probably remembers the details of the dream. It's like a specific, detailed, movie-like experience of a dream. Okay? Fatal familial insomnia is extremely rare, but that's that situation where a person stops dreaming. It's going to be in here somewhere. Let's see. Here we go. So a person stops dreaming, or stops sleeping, so also stops dreaming, kind of gradually and slowly. So it starts off as having mild sleep problems, it becomes more serious, and within a few months to maybe a couple of years, the individual dies. There's not really any good treatments for this. It's extremely rare, but does seem to be genetic. But we tend to see here degeneration in the brain. Is it the lack of sleep that damaged the brain, or is it the brain damage that caused the lack of sleep? We don't know because the sample size is so small. Okay. This is where I'm going to draw the fill-in-the-blank questions from, so make sure that you know this. But remember that the basal forebrain is going to be important for slow-wave sleep. Let me get there in here somewhere. Okay, yeah. So we know that general anesthetics produce something that looks like slow wave non-REM sleep, and general anesthetics use GABA, so we think GABA is also important for non-REM sleep when you're not under anesthesia as well. So we did these transection experiments. A brain by itself can still have all the different phases of sleep and waking, which tells us that the triggers for sleep, all the different components of sleep are located in the brain itself. And then if you isolate the forebrain from the rest of the brain in the body, you'll continue to see the non-REM sleep, but you won't see the REM sleep. So that tells us that the forebrain, especially the basal forebrain, is where non-REM sleep lives, but REM sleep lives somewhere else. Okay. All right, the reticular formation is going to be important for waking you up. If you stimulate this area, the individual will wake up. If you sever this area, the individual will go into a coma. This research was done in cats. The pons is important for REM sleep. So this is not just about the rapid eye movements and all that, but also the paralysis that you experience during REM sleep. So the subcorrelius is this particular portion that's especially important, and if you have small damage to that area, then the individual may continue to have REM sleep but not have that paralysis they're supposed to have, which then leads to the REM behavior disorder that we talk about later. And then the hypothalamus is going to be important for coordinating all of these different stages of sleep. And make sure you understand about narcolepsy that's related, because narcolepsy happens when there's a problem with the hypocretin secreting neurons in the hypothalamus. And so what happens is that the individual loses control over sleep. You're supposed to fall into non-REM 1 and then non-REM 2, non-REM 3 and REM. But what's happening here is a person can fall straight into REM sleep and have constant sleepiness or sleep attacks. So make sure you know about that. Enuresis would be bedwetting, sleepwalking. All these things are happening, well, I should say enuresis and sleepwalking are happening during non-REM 3. What am I? My brain just wandered off. Enuresis, night terrors. Also night terrors happening during non-REM 3 as well. There we go. SIDS, sudden infant death syndrome. It's a sad situation where you have sleep apnea in an infant that is then not able to recover from that and is often fatal, according to the name. Although sometimes you can interrupt, like if this is happening and a parent, somebody notices it, and you can wake the baby up, and so sometimes it could be stopped. But what happens here is that an individual is not able to breathe, so the recommendations to try to reduce SIDS would be things like having baby sleep on their back, make sure that there's nothing in the sleeping area that could get pressed up against the face, so no stuffed animals or blankets or pillows, that kind of thing, and other things, breastfeeding, pacifier use, all those things are good as well. The thing about using sleeping medications is that once you use it, you need it, and then you become tolerant to it. And then once you build up the tolerance, then you're going to want a larger dose. And so for all those reasons, and because it can lead to drowsiness and differences in your sleeping patterns, it's better to engage in sleep hygiene. Go to bed at the same time, wake up at the same time, be in the dark before you go to sleep, try to make sure you go to bed when you're tired, don't look at bright lights before bed, that kind of thing. Okay, and then to briefly talk about chapter 15, we talked about emotions being made up of what you're feeling, what you're doing, what's happening inside of your body. And so we know that the autonomic nervous system, fight or flight, and resting and digesting are important for different emotions that you feel. We talked about the cognitive attribution model, the idea that you feel something physiological, like your heart's racing, and then you look to the environment to understand why you're feeling the way you are. So we said that if you're surrounded by happy people, you might think, hey, I'm happy. Or if you're surrounded by angry people, you might think, hey, I'm angry. That kind of thing. Polygraph testing, as we talked about, is going to be lie detector testing that is not terribly valid, but is conducted still sometimes, but not admissible in court. So what's happening here is we're measuring different physiological measures, assuming that a person will have a spike in anxiety when they lie, although some people are just anxious all the time. Yes, that's me. And also some people are not anxious when they lie. So it's not a perfect method there. Okay. I just realized that part of these slides might have been out of your recording view, so sorry about that. Okay, facial expressions. So we know that facial expressions are pretty consistent across cultures for basic emotions, things like anger and happiness and sadness. But then for more complex emotions like embarrassment, pride, contempt, those facial expressions are probably less universal. But your facial expressions can impact how you feel. That if a person is manipulated into smiling, they'll probably report feeling happier. Or if they're manipulated into making an angry face, they'll probably report being more angry. And then people who are not able to make facial expressions, maybe someone who has Bell's palsy or someone who's had Botox recently, probably feel fewer emotions or less intense emotions. We talked about decorticate rage, about removing large portions of the cortex from dogs and finding that they were not able to inhibit their rage. So we're saying that the deeper structures in the brain cause the rage, and the cortex probably controls the rage. And when you remove the cortex, then they continue to feel that rage. There was nothing to inhibit it. Fear conditioning, we talked about how this can be classical conditioning, where you learn to become afraid of something that was neutral because it's associated with something that is really scary, right? So maybe, for example, there could be, I'm trying to think of a good example here, a fear, something you're afraid of would be a good example here. Like maybe I'm just trying to think here. I don't watch a lot of horror movies, but maybe there's a certain type of music. Maybe they play a certain type of music during scary scenes in a movie, and now if you hear that music somewhere else, it causes you to feel scared. Maybe. I could see how that could happen, but I don't watch a lot of horror movies. Maybe the music on Jaws. I don't know if you guys have seen the da-dum, da-dum. I mean, you could become conditioned to be afraid of certain music, sounds, smells, that kind of thing, okay? It's associated with the amygdala. Sorry, my brain's not working great to come up with great examples here. What happens if you damage the amygdala? The person's not afraid anymore, which they're not afraid of anything like environmental, like a scary movie, or you jump out and scare them, loud noises, but they are afraid if you inject them with epinephrine or if you deprive them of oxygen, they will be afraid of that. As far as influences on aggression, we know that there are certain neurotransmitters. So we talked about GABA, we talked about serotonin, how both of these are related. So if an individual has higher levels of serotonin, they tend to have less aggression, higher levels of aggression, less serotonin. Okay, so serotonin seems to be preventative here, that's what I'm saying. And GABA also seems to be preventative as well. There we go. Also, other things we talked about, like male aggression, dominance, all of that. Ted Bundy, super creepy. I mean, really, like, yeah, anyway, super creepy. Okay, alarm reaction to stress. What happens when we feel stressed out? Our body has a quick reaction that involves epinephrine and norepinephrine, and a slower reaction that involves cortisol. Epinephrine, norepinephrine, and cortisol are all going to prepare your body to handle stress. The difference is that epinephrine and norepinephrine do it quickly, whereas cortisol takes longer to kick in, but also lasts longer as well. Okay. Stress immunization. Make sure that you know that in order to have this effect, you need a combination of not just mild stress, but also coping skills, comfort from a parent caregiver. Okay. So children who are exposed to mild, note mild, levels of stress, but then comforted, cared for, they learn that they don't have to overreact when stressful things happen. So we had this research in rat pups that if they were stressed out and then received attention from mom, they were actually resilient, versus the rat pups that were stressed out and didn't get mom's attention, they were more likely to have stress problems later. Okay. Ways that stress can harm health. We talked about people who have hostility being more likely to have heart attacks. We talked about the immune system being suppressed by anxiety, stress, depression. The short-term and long-term consequences of stress reactions. There's a nice chart here. The idea that in the short term, taking energy away from other things to put towards escaping something dangerous is good. But in the long run, if you take energy away from digestion and growth and reproduction, then that's going to cause health-related concerns. Okay? Okay, let me know if you have any questions as you prepare for exam 3 or just any questions in general. Remember that exam 3 is going to be due by 5 p.m. on March 31st, and you can find this updated schedule on Canvas. All right, you guys take care, and I will talk to you in the next video.